Hey folks, today we're going to discuss the empirical rule. And this is a pretty foundational set of properties that applies to bell-shaped distributions. And we'll see shortly that another way that we can refer to that shape is as a normal distribution. And working with bell-shaped or normal distributions is such a building block in statistics, has all sorts of applications in various analytical techniques. And it's also a naturally occurring phenomenon, which I will show you in a moment. And well, the empirical rule, it's kind of a set of three components, and it can branch out into many other elements. Let's look at a little picture first. With a bell-shaped distribution, we have the symmetric distribution with the mean in the middle, y bar or x bar, and most observations are observed near that mean. And as observations get further from that mean, there's less and less of a chance of observing that observation value, and that applies in both directions. So the empirical rule sets out how likely are observations going to be observed with respect to how close they are to the mean. And the way that this is spelled out is in terms of standard deviations. So I'm going to refer to intervals. For instance, if you take the mean and you minus a standard deviation, and then take the mean and plus a standard deviation, this is an interval, and it would contain approximately 68% of observations. On this image down here, what that would look like is, I'm going to put two tick marks that are equidistant from the mean, and basically this region in between the pink dotted lines, that's about a 68% of the observations. We can extend this out if we consider an interval from the mean minus 2 standard deviations to the mean plus 2 standard deviations. Then this is an interval that should contain about, let's think about it. That's going to be a little bit further down and a bit further up from the previous pink marks. So that's going to be a larger proportion of all values. And it gets pretty tall there, 95% of observations. And the last segment of this empirical rule is, maybe you can see the trend. Here we've got plus or minus 1 standard deviation, plus or minus 2 standard deviations. This last one, the mean minus 3s, the mean plus 3s is an interval that should contain, it's going to be a pretty solid proportion, 99.7% of observations. Cool. So the empirical rule is sort of these three statements, but we can dissect it to be a little bit more descriptive. And I just want to do a quick example on the side over here before we do a detailed example. Suppose you have a mean of 10 from some data set, and the standard deviation is 2. Well, what would be the interval that the 68% is referring to? Well, that would be from 8 to 12, because that would be the mean minus 2 and the mean plus 2. What would be the interval that contains about 95% of observations? Oh, well, I'm going to subtract another 2 from that 8, but add 2 to that 12. Hopefully that kind of makes sense. Okay, let's dissect this triplet statement and dive in a little deeper. I'm going to scroll down to give myself some space here. And I'm actually going to draw another normal or bell-shaped curve here. And I'm going to make it kind of big because I'm going to write a lot in it. All right, I've drawn myself an acceptable bell-shaped distribution here. And I put some tick marks along this horizontal axis. And the one that is in the center is going to be our mean. I'll use X bar for that. And each tick mark is representing one standard deviation from the mean. So this tick mark immediately to the right will be the mean plus 1s, and then this is the mean plus 2s, and this third tick mark right there, mean plus 3s. And I'm going to follow that pattern on the left side as well. X bar minus s, X bar minus 2s, and X bar minus 3s. And as we've already noted with the definition of the empirical rule, the amount of observations expected within one standard deviation of the mean, that's 68%. And how we're going to dissect this a little further is as looking at this 68% as sort of an area in this curve. This entire region that I've encapsulated here would be 68%. But what if I were to put another little line right there? Now we have two little wedges. Can we anticipate what percentage goes into each of those wedges? Wouldn't it be 34%? So I'll write 0.34 or 34%. Awesome. That's kind of what we're going to do here for the other wedges of this empirical rule. The next segment here would be the mean plus or minus 2s, 2 standard deviations, which is about 95%. And we're going to consider the wedges right here. I think there's a way we can figure out what percentage would be in each of these little wedges. If we think about this 95%, well, we know that wedge is not 95%, but both these wedges are 95% minus 68%, which is 27%. So the total is 27%, but go ahead and chop that in half, and you've got 13.5% is the expected percentage of observations in these little wedges here. I'll type over here as a decimal 0.135 or 13.5%. That's kind of fun, huh? We're going to do this one more time with the mean plus or minus 3s. So that should encapsulate about 99.7% of observations. And hopefully my graph here is reasonably well drawn. It sure does look like almost the entire distribution is accounted for. And our question now is what proportion is in this wedge here? Well, how do we figure that out? It's going to be in a similar fashion like we did up here. We're going to take that 99.7, subtract off that 95, and then chop in half. Because we want these wedges, which is that 99.7% minus, get rid of this 95, which is 4.7. And that would be both those wedges. So split them in half to get 2.35% in each of these wedges. I don't think I can fit it here. I'm going to put a little arrow over here. That would be 0.0235. Now I said that was the last one, but can you see that there is one more region that we need to account for? That would be this very last wedge right here. Maybe I'll shade it. I'll shade it in light blue, right? It's a very small percentage, very small proportion. How small? Well, wouldn't that blue part only be 0.3%, right? Because it would be the remainder between 99.7 and 100%. But that would need to be chopped in half. So that would be 0.15%. Pretty small. And when you write that as a decimal, you have to, like over here on the left side for me to be consistent, you have to move that decimal point to the left 2 spaces. So that's 0.0015. So I think this is a pretty valuable little image here. It not only takes the 3 points from the empirical rule, but breaks it down to all the little components. And I want to show you 2 examples. First, I want to show you a GIF of a naturally occurring process. And I think it's kind of fun. Here it comes. Whoa, that was quick. It's going to go slow. So here we've got the classic plinko sort of situation where we've got the balls falling. There's a 50% chance that in any one of these intersections it goes left or right. And you'd expect most of those balls to sort of stay the course towards the center, but there is an increasingly decreasing chance that those individual balls deviate from that center. So kind of cool there. But we're going to do another example where we're going to crunch some numbers. All right, so back to this screen here, I'm going to scroll down to an example of IQ scores. A stats class would not be a stat class without an IQ example. And IQ tests are standardized in such a way that the mean of IQ scores is 100 with a standard deviation of a 10. And those scores are following a bell-shaped distribution. I'm going to go ahead and draw a distribution. Okay, I've got myself a bell-shaped distribution, and we're going to label this like we did previously with tick marks, but now we have specific values that we can use, so it's not so general. Now, since we do have some context, I'm going to label my axis. Our variable was IQ scores, so better use that. I'm going to put a tick mark in the middle. And what number can I associate with that tick mark? That would be the mean of 100. And I'm going to put a few tick marks to the left and to the right of 100 to represent 1 standard deviation greater than the mean, 2 standard deviations, and 3 standard deviations greater than the mean. And I'll do the same on the left side. 90, 80, and 70. All right, I've got a couple questions queued up here for us, and we're going to use the properties of the empirical rule to address them. First one, what proportion of IQ scores are between 80 and 120? To address that, I'm going to look at 80 here and 120. Okay. This says between. So I'm going to even shade this in-between region, just so I have a visualization of what I'm working with here. Sweet. Now it looks like a pretty solid percentage of this distribution has just been shaded, and what I'm going to use from the empirical rule is noticing that the number 80 is 2 standard deviations below the mean, right? 2s below the mean of 100. And 120 is 2s above the mean. Now I know that looks like a 25, but that's an s. So this is a direct statement essentially from the empirical rule, where if I scroll on up, boop, 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 2s above the mean, 2s below the mean, that corresponds to 95% of the distribution. So that is our solution for this first question. What proportion? 95%. Now this next question is related. You see that it has the same values, 120 and 80, but notice it says above 120 or below 80. Looking at those regions on our little figure up here, the below 80 zone, that's going to be this blue shaded zone here. And the above 120 is going to be shaded up here. Notice at the moment, the entire distribution is shaded by either something blue or green or yellow. These two questions are complementary in a sense. This is the way I'm thinking about it, because this second question is asking the exact opposite of the first question. Therefore, the solution must be 5%. However, a more direct approach to answer that question, I suppose you could go back to the graph from above and start adding. You could add the percentages from these far tails here, because that would be the region corresponding to IQ scores above 120, and this region down here would be the region below IQ scores of 80. And certainly here we have 2.5%, and over here is another 2.5%, which totals to 5%. Okay, we're going to do a couple more questions, but I'm going to clean off my space here. All right, next question. What proportion of IQ scores are between 90 and 130? Again, what I like to do is sort of color in this region where I want to find the answer. Okay, so that's 90 to 130, and I'm going to shade it in. It's kind of fun to do this actually, and it kind of just gives me a sense of what I'm looking for. It might even help guide me to the answer. So it's a fair amount of the region here. Now this is not going to land on one of those segments directly from the empirical rule. We're going to need to be a little bit more clever here. So a couple things I'm thinking about are the value of 90 is 1 standard deviation below the mean, and 130 is 3 standard deviations above the mean. And having that ready is going to allow me to go to our picture that's up above and sort of start adding up. I'm going to add up all those wedges that correspond to in between these numbers. Now, I can be a little more slick about this because I do know that from 90 to 110, I at least know that that's 68%, right? I don't need to work too hard. I'm going to take that 68% and I'm going to add these next 2 wedges. And I'm just going to verify that those next 2 wedges are 13.5 and 2.35. I'm going to add those numbers to the 68%. Here I go. So that's the 16% plus 13.5 and 2.35. Adding all of those together should get you to the solution of 83.85%. Cool. I got one more question for you, and again, I'm going to clear my space here so I can detail the way that I'm working out my answers. All right, I'm running out of space here, but let's see if I can fit this last question up in here. The question is, 16% of test takers achieve an IQ score of at least what value? Okay, so this question is quite a bit different than the previous questions. In the previous questions, an IQ or a range of IQs was provided, and we found the corresponding chance that that would occur. In this case, the chance or the percentage of times an IQ score occurs is given, and we want to know, well, what's the IQ score that gets you there? So it's sort of a flipped situation. And another thing to notice is at least. So this is referring to the top or the upper 16% of test scores. So our answer is going to be an IQ score up here somewhere, above 100. And what we're going to do is we want to add up all the wedges until we achieve a total sum of 16%. I'm pretty sure it's going to land us at 110. Because if it took us to 100, well, 100's in the middle. So above 100 would be half of all IQ scores, and that exceeds 16%. So I'm pretty sure this is going to land us at 110, but let's go double check. I'm going to extract some of those percentages from our previous image. These small percents here, 0.15, 2.35, and 13.5. I'm going to just transcribe them down here. Okay, it appears that if you take all of those green percentages, you do add up to 16%. Therefore, all of the scores above 110 are going to account for 16% of test scores. So 16% of test takers achieve an IQ score of at least 110 is our answer. And that's going to conclude our nice little video about the empirical rule.